Principle 7, raw material or feedstock should be renewable rather than depleting whenever technically and economically practicable. Here's the learning objectives, the opportunity of the sun, context and need for renewable feedstocks, and renewability of the versatility of microbial metabolism. All right, before we get into the renewables for chemical feedstocks, I'll just talk a little bit about the power of the sun. So the solar income for 1 hour equals the total energy used in 1 year on Earth. And I must admit that I found this diagram to be fascinating when you looked at the area required to power the world. And I kind of wonder now, if you were to take all the oil tankers in the world and stack them side by side, how many of these boxes would be filled up? It's interesting to think about, but the power of solar is really quite substantial. So renewable, we're talking about natural resources that can be replenished at a rate equal to or faster than they can be consumed. When you look at a petroleum refinery and you look at the product output, there's a wide variety of materials coming out, fuels, solvents, various chemicals. And when you look at a biorefinery, lo and behold, you can find the same product outputs from biological sources. I would say that when you look here, the petroleum refinery, the developments you see on the right side have occurred over the past 100 or more years. There's a lot of sophistication built in. On this side, the biorefinery, that sophistication has not yet been built in. We're very much at the early start of the biological conversion learning curve. There's a lot to be done. When you look at the biorefinery, that is the plant itself and what can come out of it, there's a wide range of chemicals and materials that are available through plant sources. And in fact, there are a wide range of chemicals that are already in production from biological sources. So this is all 2005 data, so the numbers here are likely substantially higher now. But you see there's a wide range of chemicals that are in fact already produced from biological sources. There are a number of issues with the cultivation. You have to have the right crop plant, you have to have the right soil to grow it in, you have to give it the right nutrients, the starting material, is it a seed, is it a transplant, being able to handle the plant to get what you want out of it, disease resistance. So there's a lot of factors here that need to be optimized in terms of getting the material out you want. The life cycle impacts, and then of course the competing uses of land is quite an issue now as well. Crops for fuel versus food has been talked about. There are a large number of crop plants that have been discussed. Fortunately, there are quite a few of these that will cover a large, not individually, but there are a number of these that are more adapted to tropical environments, others that are more able to grow on a low moisture area. And so there are plants that are available that can utilize quite a different number of regions and climatic conditions. Extraction of materials, there's a range of technologies. Obviously this technology is good for low level, but in terms of making industrially significant amounts of material, you need to do something with process development that will meet the needs of the industry. For example, the airline industry has set a target for the use of bio-based fuels. Obviously, that's an industry that needs a fairly substantial source of material, and it needs it on a continuous basis. You can't have any, periodicity linked to, a certain growing season or something like that. It needs to be continually available. So these are some of the issues that need to be worked out within the bio industry. And there's a lot of speculation as to what the future will look like here. We're going to go through slides that speculate a little bit. One of the things you notice here is, as far as some basic building blocks, starting materials, so starch, oil, protein, different sources of plant material have different extents of, for example, oil compared to protein, so the starting plant is very important. Another thing you notice here when you look at the molecular structures on the right is these look very different than petroleum hydrocarbons. So once again, you go back to the length of development that's been put into developing petroleum as a feedstock for the chemicals that are so widely used across industry today. That comparable amount of development time has not really been put into biomass as a source. And that's what's part of what's needed to help deliver on the promise of biofeedstocks. When you look at some of the building in of unit operations, what might a plant look like? Here's a conceptualization where you have the bottom left, lignocellulosics biomass going in. You have starch, sources such as corn coming in, and then the processing within some type of facility using various unit operations, and then the products that can come out of this type of a facility. Once again, much the same kind of conceptualization. You have different biomass feedstocks, conversion processes of various types, and we'll go through those a little bit later. And then you have various products coming out. So fuels, you have power, you have chemicals, food and feed, multi-operational facilities to generate products of various types. Again, another similar conceptualization, looking at various feedstocks, processing, refining, synthesis, leading to products. Here's an example of an integrated biorefinery. This is a demonstration process. It was quite successful for the production of both ethanol, chemicals, and power using corn plant. The corn, you have both the grain and then you have everything else that's left. That's called the stover. And this process looked at an integrated system to utilize both. The conceptualization of a forestry biorefinery, utilizing all of the material that comes from the plant crop. Lignin is a really very tough character here. The lignin is great, makes the branches stand out straight. It's a very complex polyphenolic chemical structure. It's also very difficult to work with as far as a biofeedstock. There's a number of chemicals that have been derivable from sugars via chemical and biological conversions. These are thought of as platform chemicals that one would like to get to be able to branch off and to create other chemicals. And here's the same group of chemicals looking at their chemical structures. The emergence of vegetable oil applications. So going to, for example, 9-decanoic acid and using that as a platform chemical to arrive at other chemical structures that have value commercially. Thermal conversion methods. So starting with biomass, and there are various chemical, thermochemical processes or combustion, gasification, pyrolysis to arrive at various final products. This company called Changing World Technologies, looking at thermal conversion, so taking poultry waste of various types, including the waste left over after the processing of the chickens, doing pulping and slurrying, flashing, heating and coking, and arrive at the separation oil, gas, and carbon can be utilized. Chemical conversions, so for example, starting with hydrolysis, getting to sugars and lignin, and then going through various types of conversion processes to end up with various final products. The power of microbes. As a microbiologist, I appreciate this poem, and it's something that is really tremendously inspiring to look at what a microbe is able to do. You have this tiny microbial cell, and it is able to, no essential amino acids there. They can build everything, starting from a wide variety of carbon sources. I know there's some microbes, there's some pseudomonads, that are able to build everything they need, starting with as many as over 250 different carbon and energy sources. So really tremendous power within microbial cells. And then you put that together with the high surface to volume ratio, and you can do things quite rapidly with microbial cells. Ethanol fermentation is certainly the most well-known, and there are facilities and operations in place in different regions of the world, starting with ethanol to produce various chemicals. When you look at polymers, polymers are, especially plastics, they can be a real problem. And we'll talk about them more at Principle 10. But so plastics, how do you deal with them? You recycle them, you develop biodegradable plastics, use less plastics. Well, there are a number of initiatives that have been undertaken to look at plastics and polymers. PLA, for example, starting with low molecular weight PLA and producing from that the lactide, just purified, and then goes into a depolymerization process for producing PLA. Here's a chemical visual of that process. And then the properties and uses of PLA can be used for packaging materials, using materials that are much like polystyrene. It can be used in fibers and in bottles. The biodegradability of bottles can be a challenge even if you have materials that are they're constructed of that are biodegradable. Part of it is just the accessibility of a bottle form that can need to be broken down. In some cases, it needs the high temperature conversion possible within, for example, a composting operation. Polyhydroxyalkanoates, once again, another material starting with a sugar solution, going through fermentation to PHA, and then on to plastic products. Biodegradability. So wrapping up here, there are tremendous supply needs and also scientific and commercial opportunities within the area of renewables. As I mentioned, the stage of development here with renewables very different than with the petrochemical area. Thinking a little bit about oil, it's certainly a great feedstock, and my way of thinking, does it make sense to use that large fraction of oil that we do to just convert it to CO2 to obtain energy? There's a great amount of reduced carbon in the ground. You know, is that the best way to be using it, or should we see if we can be doing more to replace that fraction of oil or fossil fuels with some other technology? And solar, it's not a quick conversion from where we are now to something like solar or whatever energy source we're going to move to. And we need to start implementing the transition to be able to be positioned so we have those technologies available when we really need them. And biorefining can likely match a great number of the chemical feedstocks we need and match most of what can be produced by petroleum-based refining. Okay, so with that, questions?
I've wondered about biodegradability for a long time. What are the main advantages of having it? Not you're effectively using carbon sink, just what are the why are we supposed to survive?
Well, there's a couple of ways to look at it. So one way to look at it is when you have a compound that's biodegradable, it takes that exposure piece out of the risk equation. So if it's biodegradable, it's not going to be available to expose a target, and if it has any toxicity associated with it, that goes away. And that's probably the biggest piece, the most, well, when you look at plastics, and I'll show some slides about this and other compounds, and you look at what's building up in regions of the ocean, I mean, plastic has certainly a lot of visual hazards. It has entanglement hazards to wildlife and quite a few others. So biodegradability, removing and recycling the elemental constituents is a good thing. But certainly toxicity is a big thing. For example, surfactants, branch chain surfactants that were used years ago, foaming and other toxicity hazards. Yeah. Yeah. There's some papers that have been out recently talking about plastics and plastic fragments in the ocean as sinks for attracting, sorbing the toxics that are in the water column and actually concentrating them, and then they can get consumed and build up. Other questions?
Going to microbial conversion, do you think that it'd be worthwhile to look into ethanol and butanol production as a means of formidable energy production as a source for global energy consumption? Or do you think that that's not worth
I'm going to, since
economic?
Dave just talked about energy, I'm going to let David answer that question.
So the issue with most of the bio-derived ethanols, or ethanol or butanol, is where your sugar is coming from. So I'll be controversial and will say that corn-based ethanol is not a good idea. Cellulosic-based ethanol or butanol, biobutanol, is probably a better idea. But we're still in the issue with any crop is all of the agrochemical impacts. So remember at the very beginning I said you trade impacts. Where in the life cycle do you want to trade the impact, and what impact do you want? So land cultivation has a lot of issues in terms of eutrophication, which is nitrogen and phosphorus going into waterways. And that's a huge issue. It's erosion, and then competition of arable land. So that is food for food production versus fuel production. So if you balance all those things out and you can do fuel production and not impact food production, and you can do it at higher levels of conversion in terms of the overall efficiency, then it makes sense. Are we there yet? No. Do we have a pathway to get there? We're working very hard to get there.
Yeah, and everybody else can hear.
All right, so there's a lot of, and we see more of this in California maybe, but also in the rest of the country, there's been a lot of controversy about genetically modified crops and that sort of thing recently. Is there research going on towards using genetically modified biofuel type crops? So you're looking at something where it's not going towards food, and is that something that people are looking at, and is that something you see a future in?
Yeah, I would think so. I don't know specifically about the activity, but I can't imagine that it's not.
The fact of the matter is that synthetic biology is the future. And so in your lifetimes, we'll see animals changed as production. So they will produce drugs and other things from animals and other materials. From a whole series of platform, bacterial, fungi, and a host of other organisms, they will be producing chemicals and fuels. So cyanobacteria has been shown to be great for getting CO2 from and converting that directly to a fuel. So I mean, there's multiple platforms. If most of the world knew what synthetic biologists could do and are doing, I think they would be a little bit scared. That isn't to say we shouldn't do it. It's just that these things are happening. That's reality. It's already occurring. What is slowing it is the transition from a bench scale to bricks and mortar and not having